recording. So it's on video. You have video evidence. So yeah, second to last lecture. We're going to review for the final for these last 2 lectures. And before we get started, I just want to say I released this. This is the last week of classes, and that's what I promised on the first day of class and or the syllabus somewhere. I will accept late assignments until this Friday, right this week. 11:59 p.m. You can turn things in late for half credit. All right. So that's the cutoff date for everyone. If you missed an assignment, it's better to get 50% than 0%. So complete it to 100%, and I'll give you half of that. All right, once you submit it. So this Friday, 11:59 p.m., the last day to turn things in late. All right. Any other questions about logistical things? Do you remember when the final is? We got that coming up too, right? It's the Monday, right? Yeah, it's on Monday at 3 of finals week, so that's exciting. So next week, 1 week from today, 7 days, right? We'll be in this room right now taking the final. All right, that's exciting.
Is that on syllabus by chance?
The date of the final? That should be, yeah, that's on the syllabus and the little whatever it is. It's like a table of important dates. It should be there, yeah. So that's there. It's also on the final info page. So yeah, those are all there. Let's do attendance before I forget about that. 2 more attendances. So please tell me you exist, and I think that was everything I wanted to say before we got started. Any other questions about anything? Or we do? Yeah.
So the final is the same format as the midterm, correct?
You can expect a similar format to the midterm. Yeah, I'm going to write similar kinds of questions. Yeah. Yeah.
Do you still drop the lowest 2 assignments?
I do, and Canvas should be doing that automatically right now. It should be like highlighting some of your grades or putting a little dot next to them saying like this is not counted towards your final grade right now. So yeah, let me know if you can't see that. But that's also a promise I've made to you, and Canvas should be doing that automatically, that dropping of lowest scores. Yeah. Good. I think that covers most of it. Let me open up the slides at least. Now we'll get started. Did this carry over? Yeah. All right, so I've made a new file called final-review, so it's not like chapter or anything. We'll call it final-review, and that's where I'll put everything for today. So yeah, if we're good, let us begin. And the very first thing I want to talk about is let's go over midterm 1 stuff. Let's be very confident about our use of the tables and all the other functions and operations that we learned from midterm 1 time, so that we can apply them well for sorry, not midterm 1, it's just like midterm, excuse me. In other classes I have multiple midterms, but review of the midterm. Technically it was midterm 1. So here's my silly example. I've got a list of census data for every city, town in the United States, and then their median income. So I've got that piece of data, and we're going to read from that. And then also I've made a list of every single Trader Joe's location. All right, so this is going to be where we're going to answer this question. Where should I retire? Because all I want is to extend my pension amount from the school, right, and make it last as long as possible. And I also really like Trader Joe's products. So that's all I want when I retire. I want to live near a Trader Joe's, and I want to save money. So I've got those 2 data sets, and we're going to combine them, okay? That's what I want in this world. So, okay, where should Lawton retire? Let's find out. We're going to notice that the question is harder to answer than we think it is. We're going to get some final data, and then we're going to have to think about that data. But I've got a few tables in this data folder. I've got the first one is, I added it recently, US-median-income-2023. So that's the last time they made some estimates in 2023. The median income for pretty much anything, any place you could have marked on your census when you take that. So I'll call this table income. So table. Read table, data, US median income, and it looks like this. Yay. So they also have just every state in general, like here's the median income in California. But the first 50 rows plus a little extra for Puerto Rico and Guam and all the places that aren't actually states but are whole places. They have those at the start, and we kind of just want the cities, so we're going to get rid of those in just a second. But do remember that you're going to have access to this page and also this page. and all the things we're doing are more or less on there. All these table things. We're gonna take a few rows off the table, so we're gonna take some stuff. Take some stuff later. That's gonna be our game. So let's cut this off to be, I don't know. Let's take just let's take some rows. Income dot take. Let's start at like np.arange, because I want every row after like the first 50. I don't want the states. I want just the cities. So it starts like this. So let's do np.arange, where let's start at like number 0 through 49, right? So 50 is the one after all the 50 states in theory. So let's start at index 50 and then go until the end, just like 32969, I think, because there's 70 really, because it shows the 10 up here. So go up to there. It's really just like go until the number of rows minus 1. And so it's up to the number of rows, income.numRows, but not including that last one. And that's what arange does for us. So this is going to give us a bunch. And you see how some of them are still there. So we got Wyoming and Puerto Rico. And then it starts with cities in Alabama. All right. So I want to get rid of those as well. So this was index 50 up to here. So 51, 52. So this is index what? The original index would have been 50. This would be index 51. We want to start index 52, let's say. Let's make the income table that. And then we got just a bunch of cities. And for weird reasons, they add like whether it was a city or a town, even though that's not the real name of the place. It's like to mark what it was. Some of them are CDP, which stands for Census Designated Place. It's like not a city nor a town, something even smaller. So let's call that income instead. Income, only the cities, please. And that should be good. Okay. And so we can look up Fresno, like we can see the median income estimate of Fresno in 2023. That would be a dot where, right? A dot where. So here's what income looks like now. We just want to search for geographic area name having Fresno in it somewhere. So that's income dot where, like the geographic area name column, or just column index 0. The values there are something Fresno. I guess we could say Fresno space lowercase city, comma, California, but that's too much work. We can look at these and think of like what's a good one for us to be using. Equal to, can't be equal to because it just has it in it. Above or equal to, below or equal to, between or equal to, contained in, almost, containing, right? Where the geographic area name values are containing the string Fresno with a capital F. And that will tell us what we got here. There's a bunch of different Fresnos. So apparently there's not some cities or towns where there's census designated places in Ohio and Texas. Crazy. But there it is. And there's our median income estimate. The other big city around here is Clovis. So there's apparently a Clovis, New Mexico, and there's also Clovis Community College in New Mexico, which makes it very confusing. They got clovis.edu, unfortunately. They got it too quickly. We had to say cloviscollege.edu, sadly. So yeah, that's all that stuff. Yeah, don't forget how to use .where. It's going to be very important on the final. But you see that sometimes the median income estimate, like if I want to do math, right? I want to like sort by this stuff. Right now it's just a bunch of strings because some of these columns have dashes, unfortunately. Some of these columns, like the median income estimate, there wasn't one. So they just put a dash in the data that I got from the government. And so we kind of want to get rid of all the dashes and other things too. There are a bunch of things that are not integers. And so I kind of want to like take this column and make numbers out of all of these if we can. But if we can't, just like put -1 or something so I can still do number stuff on them. Does that make sense? That's what I would like to do. I want to make essentially a function to apply to this column, right? That would turn everything that's not a number into -1. All right. And so the function that lets you do that, it's like here, income dot apply. I want to make a function like called fix, and I want to apply it to the median income estimate columns, like column number 1. The function that I'm about to make called fix, I'm not going to test you on the thing it's going to take to make that work, but I'll just show it to you and explain it as I go. You can look into it if you're interested, but I kind of want to do this. Income equals income dot with a new column, also called median income. Like I want to overwrite this one. Median income estimate, overwrite it with this resulting column where I've fixed them all up, made integers out of the ones that are actually integers and made -1 out of the ones that are not. It's like, that's what I'd like to do, please. And the function that's going to let me do it looks like this. So I'll call it fix, and it's going to take a value called x, and like I want to give back like the integer form of it if I can, because by default right now, because there are dashes potentially, like it just made the whole column a bunch of stirs, sadly. And it's like I want to turn them into integers when I can, but sometimes this int x thing is not going to work. Let me just prove that to you. We see it's just not going to do the right things. Like I don't know how to convert a dash into an integer. It's very confused. So sadly, that's not good enough. And so what we can do in Python land, which you do not have to understand at all, is we can say, hey, Python, try to do this. Try to do that if you can. Otherwise, except when you can't, say -1. It's kind of like a weird if else. I'm not going to test you on this idea, but this is what we need here. And so this should do what I want to do, and it will run. All right, so I fixed up all the columns. If I can make an integer out of those data pieces, like when they're actually numbers, do it. Otherwise, when it can't, make them -1. So now I've got a bunch of -1s instead of a bunch of dashes. So if I said Fresno again, in theory, cool, now I got a -1 instead of a dash. Now I can do number stuff, right? I can do between, I can do above, all those .where things that are nice. So we can look at a histogram. That's probably the first thing you'd want to do. Like, oh, I got a bunch of income data. Let's look at a histogram of the United States. So let's do like, let's do income dot, give me a histogram of the median income estimate. So that's column 1, right? Do that. And I got a bunch of -1s now. And also the bins are weird looking. We can say, comma, give me like 25 bins, right? That's a little bit better. The unit is dollar. You want to be like that and be very precise. But there's a lot of -1s and they're right here. All right, it's not looking great. So let's do this histogram for all the places where we actually have data. So let's do a .where on income first, and then do a histogram to show me the median income estimates for all the cities that actually have income data. So where the income.where the median income estimate values, or column 1 values, are between or equal to, like go from 0 and go all the way up to, it looks like 100,000 is a decent number. Some of them are much larger for very, very wealthy communities, but let's just deal with normal numbers. I think that would work out. So up to 100,000 there, that looks like a nice looking histogram. All right, so we can see that Fresno, 33,000, is right about at the median income estimate. See that? That's kind of interesting. So we're smack dab in the middle of everything, it seems. So yeah, that's the income table. Any questions about that? You see how we might explore that more? That's fun. And then I've made a table of all the Trader Joe's locations. I just went to their website and scraped all the pages. So I'm going to say table.retable Trader Joe's, and I'll call that TJ's. And so here is just a table with one column called city. Here's every Trader Joe's that I could find. All right, cool. And yeah, we need now to be able to like combine. We want to look up one of these cities in this table, right? I want to do that. Like I want to take Birmingham, Alabama, and go look it up here, and it's going to be called, well, first of all, in the other table, Alabama is going to be spelled out, and it's also going to be called Birmingham space lowercase city, isn't it? That's going to be a little weird looking. So we need to get those two pieces of data, like these two city names, to correspond in a way. All right, so I can look them up together. And so let's take the Trader Joe's table and expand it into city and state. And let's take the AL and expand it to Alabama. Let's take the AZ and expand it to Arizona. Let's do that. Okay, because then that would allow us to look it up in this other table. That would make sense. So the way to get there, like there's a Fresno, CA, because there's a Trader Joe's in Fresno, right? I want to take this and I want to get the Fresno and I want to get the CA out. Did we go over that once upon a time for string stuff? Yeah, we did a string.split before. Did we do that? I think. At least maybe you've used it in an assignment. So if you have a string, you say .split, and it will turn it into a list, which is just like an array. It's a sequence of things after it's split based on that idea. So if you want to split this text based on the dot, it will just split it up into everything between the dots. That's kind of neat. So if I take Fresno, I can say split on the comma, because the comma is what separates the city name and the state, right? It will give me back this, Fresno, and then it's space CA. You see that? Space CA, but you can fix that quite easily. You could have also split on comma space, and then I just would have been like, all right, in between the comma space, I can get that and that. But let's make it harder for ourselves so I can show you some more functions. Well, there's that. I can get back a sequence of the city name and almost the full state, right, with an extra space there. So to take a sequence like this, take a list, there's no .item on lists, unfortunately. You could convert it to an array if you wanted to, but make array is not going to work properly. You have to use like np.array like we were doing in chapter 17. If you want the first thing, you got to use these square brackets. I want to go to index 0, item 0, you do it like that. So this results in this sequence. If I do item 0, it'll get me out the Fresno. Okay, that's what's going to happen. So give me that. That gives me that. And so if I go to item 0 of that, with that syntax, I get out the string Fresno. That's perfect. I can make a function that does that and get the city name out of everybody now. I can do the same thing with index 1 to get the state name almost. But that has an extra space at the start because of the way I did the splitting. There is a nice little function on strings, on strs, that is called strip. You just say .strip on the resulting string. It strips away all the white space on either end, which is nice because that's usually something that happens when you're doing this kind of thing. And so that will give me the California by itself. Yeah.
Strip was automatically cancelled anyway, please, in the middle or anywhere?
On the sides.
On the side.
On the sides only. So it's like if you had hi mom. Oops. Strip. It's not going to do anything, but it's if there were spaces around here on either end. That's what it does. Yeah. So it's solving this exact problem and not trying to take spaces out of the middle because you probably wanted them there still. Yeah. Good question. Other questions? Like I won't test you on strip, but like this is what we need for this problem. You go looking up things you need to solve the problem at hand. It's a great example of that, I think. So yeah, that'll get us out to California. And so with this knowledge, I can make a function that like gets the city out and does this kind of thing. I can also make a function when I apply to this column. I can do this thing and get the state out. That'll be nice. Okay, so let's do that. So I'll make a function called, because I want to apply it, right? I want to say, I want like a get city function. So you give me a string, I'll give you the city part of that string. That's this thing, right? Where S was the, like Fresno, for example. That will give me the city part out of a string called S, yeah? And I can do the same thing for the state. Get state. You give me a string called S, and I'll give you back this idea. Or it's not Fresno anymore. We're going to do S. It was generic. So that's, you give me anything that looks like that. I can give you the city out, I can give you the state out, and I can apply those kinds of functions. Okay? So that will get us most of the way there. If I apply these, I'll get Fresno in a column by itself, and I'll get CA in a column by itself. But I want to turn the CA into California, because that's what this table wanted, right? They're all spelled out. And so I've made one more table called state abbreviations. That one expands it, all right? So here it is, table, read table, data, state. I need 3 tables to solve this problem, to figure out where to retire. So I'll call it state abbreves, I guess. And so here's a nice little table of state names and their abbreviations. And so I kind of want to look up this, find the CA, go here, and turn it into that other column version of it. Does that kind of make sense? I can make a function that does that. You give me this, I'll look up using this table and give you back the California. Because that's all we need at that point to make it work. So, dun, dun, dun. So this is not really get state, is it? It's get state abbreviation. Let's call it that. Let's make another get state that gives you the full state by starting with, dun, dun, dun. Let's do the same thing. Like, let's make one called get state. First, get the state abbreviation, because, gosh, how do I want to do this? Because if you got the CA, right, you can go look it up here. Go to state abbreves dot where the column 1 values, where the abbreviation. You could say it like this. Abbreviation values are equal to, right? You could say equal to CA. That would give you this, right? You could have said R equal to is, that just defaults to R equal to. So you could have said like where the abbreviation is CA. That would give you this row. And then you want to get the, let me give you this table back. You want to go to row 0 of this table, right? And column 1. So there's a bunch of different ways to do this. Go to row 0. And then I want the name part of it. I want the full thing. So I can say dot item 0. So you give me CA, I can kind of make some function that generalizes this and turns it into California using that table. Does that kind of make sense? That's what I'd like, because then I can have my Fresno, I can have my California all spelled out, and I can look it up in this income table. That's what it needs. So, all right, let's make an actual get state function now. So you give me a string. I know how to get the abbreviation for that state. I can get the CA out with this function. So let's do that first. I'll use my get state abbrev function on this S, like Fresno, comma, space CA. That'll be a state abbreviation. And then I can take that state abbreviation and do this to it. I can get out the actual state that it corresponds to. And so it's not CA anymore. It was whatever state abbrev was. And return that. Okay. So that should do it. And so now I have a get city. Get city called on Fresno CA gets out Fresno. We had that already. And now get state. We had get state abbrev. Did that. And then get state abbrev was used in get state to give me California. Now I can combine the two. Does that make sense so far? A lot of plumbing necessary to get this to work. But we're ready. All right, so this is what our Trader Joe's table looks like. All these values. I would like to apply now to this column twice. I'd like to apply my get city function to this column to get the cities out. I'd like to apply my get state function to this column to get the states out. I want to put them next to each other. So I would like to make another table, right, with the following columns, right? Where city is now, I want to make city comma state. So city is equal to the Trader Joe's table dot apply. And I get city function to, well, it's the city column. I can spell it out, or I can say index 0, column at index 0. I want to do the same thing to get the states out. State. And this is going to be get state. And that will give me, once you let it run, this table, and now I've expanded everybody. That's lovely. Does that make sense why we needed that? That's quite nice. I could just call this Trader Joe's again. I can call this TJ's. Let's say Trader Joe's is that now. You do have to be careful. You can't like rerun this cell twice. So now that's my Trader Joe's table. And now I've got that one and my income table. And they're looking so close, right? I just kind of want to do this, look up Phoenix here, look up Arizona in this column. It's just one big column where I want to look up that and that, yeah? Or we could split this again on the comma if you wanted to. That's possible. So, yeah. So, like, let's say we did want to look up Phoenix. We want to find, all right, there's a Phoenix, Arizona Trader Joe's. What's the median income estimate for Phoenix, Arizona? We'd have to do it this way, right? Income.where. So we can get out the Phoenix, we can get out the Arizona. We don't have them together in this table. We've separated them on purpose, though. So like we want to do like where the geographic area name or index 0 values are containing, like, you gotta do it separately. Phoenix, it's OE, right? Phoenix. That would give you all the Phoenixes. There's probably more than one Phoenix, right? Of course. So you want the Arizona Phoenix. So again, you'd whittle down this table even further by saying, all right, take this result and then also do a dot where where this is containing the right state. Does that make sense? Yeah. Yeah, here, do you want to just me to give you this code right now in the code from class?
Yeah, I mean, I just need to look at the TJ to see how it looks.
This one?
Yeah. Okay. Just want to make sure that it's correct.
Okay, yeah. Yeah, if you want it right, I can just give you what we've done so far if it's been too much typing, because it did go fast. Whee. We got a lot to cover. So yeah, there, if you want to refresh the code from class page now, you've got everything we've got so far. So yeah, we've got all those things. And so, all right, if I want Phoenix, Arizona, then we gotta whittle this down one more time. Take this and then also do another dot where that column 0 geographic area name values are containing also Arizona. And that will give me that, right? That will give me that, and that's perfect. And I kind of want to get the median income estimate out of that, right? I want to extract this guy. So I can put it next to, like I want to take this Trader Joe's table and attach another column where I put the median income for all those cities. Does that make sense? That's my goal. That's my goal, because then I could sort by that. This is all the Trader Joe's. I can sort by that now. So that's kind of what I want now. So, all right, I can do this to extract from the income table. You give me a city name and a state name. I can do this kind of double where to get the right place. And then I can extract, like I can go to row 0, or I can do it backwards again. I can go to column 1, index 0. We can do it that way. Or I can go to row 0, index item 2. That would work as well. Whatever you'd like. So let's make now a function that you give me. Like, we want to start from Trader Joe's, right? You give me a city name, you give me a state name, I will give you the median income for that city and state using the income table. So I'll call it like this. Def get median income. You give me a city name, you give me a state name. I will go and do this exact thing and give you back the median income for that place. All right? So let's see here. So like you can do this for that city, or it's not Phoenix anymore, just like whatever city you gave me. It's not Arizona anymore, it's whatever state you gave me. All right. So that's like a results table. And unfortunately, the way that Trader Joe's marks where their stores are, sometimes they're a little bit too specific. They're more specific than the census wants. It's like, I forget which one is going to mess this up, but it's like there's like a Trader Joe's in a certain part of LA. Let's pretend it's like Echo Park or something. And Echo Park is not on the income data anymore. It's just like it was supposed to be Los Angeles City, California. And so I don't want to do that kind of thing. So sometimes we're not going to find anything. Sometimes we're not going to find anything when Trader Joe's was too specific. So let's just play the game of like, all right, if there are no results, let's just say it's -1, and we can look it up later manually. We can figure that out. So sometimes this is not going to work. But if it did, you could be like, all right, taking my results, return, it's results dot, like you got this guy, go to the median income estimate row and get this first thing out. Like that's the first and the one and only row should have your answer, right? So go to column 1, item 0, because that would go column 1, all these, item 0, the first thing should be the top of the list and the only thing on the list. Like that would, in a perfect world, that would work. Okay, so there's that. And so I could then attach and be like Trader Joe's with a new column called median income, where I take Trader Joe's and apply my get median income function, median income function to the city column and the state column, which is 0 and 1, right? Column 0, column 1, right next to each other. Or I could say city, comma, state. Either way. Either way would be happy. And this would work, but sometimes this results table is not going to have in item 0 in its column 1. Sometimes there aren't going to be any results because they used like a piece of a city that was in the census. So it's not always going to have, you're not always going to get results table populated with stuff. So let's do an if else. That would make it easy. So if results has a row, dot num rows is greater than 0, then you can play this game. You'd be like, all right, go to column 1, item 0. That's fine. You actually have something to return. Otherwise, if that's not true, just be like, return -1. We can look at the -1s manually later. And now this will be happy. And I should call this like TJ's with income. That's going to take a second because it's got to do a lot of back and forth. So like that's the resulting table. If you see it, let me rerun it so that I have it with a name now. Nice. Look at us. Look at us go. So there's all the Trader Joe's with median income data attached to them. We're almost ready, right? We just want to sort this now. We just want to sort it now. Are there any questions before we do that sorting? You see how we got here? It's a lot of weird cleanup stuff that we had to do, and that's going to be the day-to-day as a data scientist. Was very necessary. Had weird data that looked one way, like we had the state abbreviation over here, we had the state spelled out over here, we had to reconcile the two. That was very necessary. We got data from different sources, they were ordered in different ways, they were doing different things. We have to be the glue, okay? So yeah, let's do a sort. TJ's with income dot sort on median income increasing. Moment of truth. Let's sort by median income. And there's a lot of -1s. Oh shoot, did I do something wrong here? Yeah, Fresno shouldn't have a -1. I'm sure I did something wrong. But a lot of them worked, in theory. But yeah, you've got a bunch of -1s where some things, like, they weren't actually there properly. Fresno should totally be there. Why is that not happy? So I could have done something slightly off. Let's find out. So I was doing that with city and state. So here's Fresno. And we had, and the state was California, right? Oh, because we didn't do the cleanup properly, right? Sometimes you get this, and so we would have had to fix that somehow. Like go in, maybe you could sort and make sure it says city. But yeah, I guess Fresno is an outlier here, unfortunately. It's like we can't get the actual data because there are two things with Fresno in it in the way that we searched for it. Oh no. So yeah, that's unfortunate, but it happens. So we'd have to go back and like clean up some of these other ones, like Chatsworth. That was the one. This is apparently like a suburb of Los Angeles, and that's not in the income table at all. So like you have to go and manually replace that with Los Angeles. So that is an issue. Like North Hollywood. There might be just a Hollywood, but definitely not North Hollywood, probably. It's like La Jolla, that's a suburb of San Diego, right? So those are all things. So you have to fix that and change it around. But it's kind of working. So there are ways to make this better, but you could, just to like get a good view of the land, be like where the median income values, like where it worked out, where they weren't -1, where we actually found something, where the values are like above 0. And then if we sort, and then if we show like a bunch of them, because I want to look at a lot, show 25 of those. It's like, here's actual things working. It's great. So here's a bunch of values, and this apparently implies that I should retire and live in Fairfield, Connecticut. But unfortunately, that's not the full story, because there are a bunch of -1s that we have to clean up. And then also, that's like the moral of the story is like your job is never done as a data scientist. You have some good job security. The first, this one, I had to look it up, Fairfield, Connecticut, and also I think you could imagine State College, Pennsylvania. These are cities or places populated almost entirely by college students without incomes. Just like, I don't know, they've got student loans, they've got money from their parents, I don't know. So they're living with not a lot of actual real income. But like that's where they've marked that they live on their census. So like you'd have to also exclude those. That's not, or I guess it means that the rent is okay maybe over there. It's still useful. But yeah, like the first two for sure. The first two are cities or like places containing only college students. And so that's bringing down artificially the median income of that area. So I would say that like Michigan, East Lansing, Michigan is probably like that's the first real one. But there's also probably that could be a college town for all I know. I don't know much about Michigan. So those are things. College Park, you can imagine as well, right? Mesa, Arizona. I don't think that has a college in it. Very honestly, I have no idea. But those are options, right? So now I know where I could live. Same thing with San Luis Obispo. You know that college students are bringing down that number for sure. If you want to own a house in San Luis Obispo, there's no way you can only have this much money. So crazy, but interesting in the same vein. We have some new knowledge. We would have to like filter it out further if we wanted to do more with it though. But I think that's a good example of like all the stuff that we need to know just to deal with table stuff and like answer questions in our own mind before we do more fancy like hypothesis tests. And that was the topic of everything after the midterm. Okay, so I think that was a good start of everything. So that was a review of midterm topics. Did that make enough sense? So like functions were big. Like we gave a bunch of examples of functions that was useful. That will be your life. But and then also table stuff. So I think that was a good review of all those things. Are we ready to move on? Stuff after the midterm. Stuff, chapter 11, 12, stuff like that. Let's try it. Yeah, I have some highlights from all those chapters. You've seen these examples before, but we'll just go over them again so we can remember them. So now that we have like the ability to deal with tables and wrangle ideas, we also learned about sampling, right? That was another thing that was technically part of the midterm one, or the first and only midterm. So we have some ideas. We can test those ideas. We can test those hypotheses. So our first example was, one of the first ones was Gregor Mendel, who grew a bunch of pea plants. He was like, I'm going to found the field of genetics. So he grew this many pea plants, and he found that 705 had purple flowers, and that was almost 75%. And he was like, probably nature deals with 3/4 rather than 7,589 over 10,000. He probably thought like, 3/4 is probably a better number. This was probably what it was supposed to be. I just saw something a little bit off from 75% exactly, just due to randomness. Okay. Or that's what we can view it. That's the lens through which we can view it as data science students. He's like, this is what he thought. I think that there's a 75% chance that if I grow a pea plant, it will have purple flowers, and a 25% chance that the flowers will be white. Those are your two options. Regardless of the colors of the other plants, like nobody's influencing anything else. And so we can turn that into hypotheses, right? Something that we can do some simulations with is our null hypothesis. That's under the assumption that there was nothing special was happening. It was all due to chance. Nothing else was a factor. Nullness, zero, nil. There were no other ideas affecting us. It was just pure chance that we got something different than what we were expecting to see, right? So that's our null hypothesis where, all right, we'll assume that his model, his idea of the world, it was a 75-25 split exactly, and that extra 0.89%, is not too much, was just due to random chance. That's just how the world worked that day. So that's okay, all right? So that's the null hypothesis, and we can totally generate some example runs of pea plants with this exact percentage chance and see what happens. We can totally do that. That's simulatable. And then the alternative hypothesis is the idea of like you're bashing down the null hypothesis. You're saying that no, there was something else afoot, right? It was not the case that his hypothesis was correct. It was not a 75-25 split. There's something else going on there. It's not the same, all right? And so when we're doing our simulations, we need like a number to compare ourselves against, because we're going to virtually plant some pea plants right now and see how many were purple, for example. And if it wasn't 75%, like what was it, and how far off from 75% was it? That's kind of how we're going to do our game. So let's pick out the purple flowers, because the opposite of purple would be white. And so we can just pick one or the other. Let's arbitrarily pick purple. That's what we did, right? So let's pick the purple flowers out. And it's like, all right, we're going to plant some virtual pea plants right now. And we're going to see how many of them were purple. Assuming that this was the split, we can virtually plant things with that exact idea in mind. And we can see how many were purple. And so we'll get like, I don't know, we'll get a certain amount. Maybe we got like 76 0.8% of them were purple. We're going to subtract that. We want to see how far off we were from Mendel's idea and see if that was like due to chance, if we could have a value due to chance, right? So if we got this value, we're going to measure the difference by subtracting from like 75%. And we'll also take the absolute value because maybe when we virtually plant our pea plants, it wasn't like 76.8, it was like, I don't know, 73.2% of them in our virtual garden was purple. So we want to see how far off it was from the exact value that Mendel thought it was in either direction. Do you see how either direction is fine here? It's like, was it 75 or was it something different? Because that's kind of what our hypotheses are implying here. Does that make sense? So it's not like, was it bigger? It's, was it somewhere away from 75? Because that was what it was supposed to be. Okay? So that is going to imply absolute value, and I hope you can see that because it's very subtle. It is quite subtle to make that observation, but that's what we need here, okay? Because it was 75 and it wasn't anything else. That's what we're kind of assuming. So anywhere around 75, above or below, we count that as away from it. And so absolute value just tells us, was it away, was it close, okay? So that's what we want, and then that will help us calculate p-values, which we'll go to next. So let's load in Mendel's proportions. I'll make a new little slot for that. So it's like the first key thing that happened after the midterm. So we can make an array, right? And that's what we need to do. We're gonna call sample proportions. That's what we need to do here. So do you remember how to do that? Sample proportions takes the size of your garden, for example, sample size, and then the proportions of each thing. So we're gonna have proportions that it's like a list or an array that add up to 100% or 1. And it tells us how often one thing was one way and the other thing was another way. So our proportions are 75-25 split. And this will, like sample proportions, lets randomness take over, like assuming that we were drawing from this model proportions, we're not ever going to get exactly that split. And so that's going to let everything be up to chance. So our 75-25 split looks like this, and that can be an array. We'll call that the null proportions. The proportions that we're assuming like the null hypothesis, the Mendel's model is going to like generate. I guess we probably said Mendel proportions actually in I think that works as well. Like that's what he's assuming. Mendel, that's what we're assuming. Mendel proportions is that, and we're gonna deal with like purple or white because it like one is 100% away from the other. Like you just subtract. So let's deal with purple. Our Mendel proportions purple is it's just the 75, but just like the fancy way of getting there is like take that, go to item 0. So those are the things. And if I say sample proportions on how many pea plants? 920 something, right? Go here. 929 pea plants. Using these proportions that we're assuming is correct from Mendel. What we get back every time we call it is, all right, we grew 929 virtual pea plants, assuming these were the proportions of purple and white flowers, and like randomness took over, and we got a little bit more purple this batch. Does that make sense? That's what sample proportions does for us. It's letting randomness take over. It's like flipping coins where you're more like your 75% chance of landing on purple and 25% chance of landing on white. It's never going to be a perfect split. If I rerun it, this time I got more white flowers than Mendel thought we should have. Fewer purple flowers, right? But they're close. They're close, and that's what it's doing, okay? So we want to run some simulations. We want to plant a bunch of virtual plants and see how often, if it was really just due to randomness, that's what we're generating here. It's like a garden that is white and like using these proportions, and all the differences really are due to just randomness. Let's see how far off we could get from like what Mendel actually saw, what he observed, right? So we would like to do the following. We would like to do a we want to get a like proportion of purple. When I call this, right, I'm going to get a proportion of white and purple, right? So here's purple first, then white. Let's pick purple for fun. We can compare against 75. We could have just picked out white and compared it against 25. Either way works. So let's pick out the first one. That's what we did before. So like that's item 0 of this result. And that's going to be our sample proportion of purple. Right? For my same sized pea plant garden. Give me the sample proportions of that. Item 0. And then that will give me like this value. If I rerun the cell, of course, it'll be different. And what I want to do is see how far away this was from what we thought it was supposed to be from 75, which we've saved in 75%, which we've saved in Mendel proportions purple. All right, and that will give me a distance. So minus Mendel proportions purple, but also do an absolute value. That's what I want to do each time. So every time I make a new guess, see how far away it was. See how far away it was percentage-wise of from the actual thing that we saw. And this is just letting randomness take over. So randomly, we're about 0.3% off. Randomly, we're about 1.6% away from 75, just due to randomness alone. See that? So that's what we want. And we want to run a bunch of those simulations. That will give us, this is a simulated distance that we're obtaining right now. Does that make sense? We're simulating a pea plant garden. We're seeing how far away they were from Mendel's guess, his model, of, all right, it was a 75-25 split. So we'll call this 1. This is what we did before, right? 1 simulated distance. So run this function. I will give you 1 single simulated distance for 1 virtual pea plant garden. No, sorry, I have to say return. Excuse me. There it goes. And so you run it a bunch of times, you get different values. So this one was 3% off. Crazy. So that will give us 1 distance, and we want to see how far away, like how often does just randomness, because this is randomness taking over and planting the garden and seeing the differences there, how far away does a random garden kind of predict what Mendel saw? That it really wasn't 75-25, it was like 0.7589 and 0.2411, something like that. Okay? So this is the observed percentage. We can do a observed distance as well. How far away was this away from 75%? Because like that's what we want to see how often randomness generates that far away distance. So that was our observed distance. We can call it that. And then we subtract 75%, of course. And we know it was a little bit bigger, so I don't have to use absolute value. But if you wanted to, you could. So like it is that value. So how often, it looks like randomness is sometimes going even a little farther away. That's good. That's giving firepower towards the idea like, okay, this could have been just due to chance. It really maybe was an exact 75-25 split. That was the correct proportions. Just randomness took over and gave us slightly different results. So that's great. And so we want to generate then a bunch of different distances, seeing how often randomness, a random virtual pea plant garden, is going to give us like different proportions away from 75-25 splits. How far off could it be? All right. So we'll do this. The more the better. Well, we'll do it like, let's do it 1,000 times. Probably 10,000 is even better. But we got places to go, people to see. So I'll say, give me 1,000 repetitions. And I'm going to keep track of a bunch of simulated distances. So I'm going to make an empty array called distances. I'm going to add to it each time. Okay, so remember, to add something to our distances array, it's np.append. Here it is, np.append. And that generates a brand new array. So if you want to like add one thing to the end of an array, like if this was like you added one to it, 1,000 to the end. If you want to put this back in the same array, you say new array equals this result. So that's what we got to do here. So we're going to say, all right, for a bunch of values. So for I in np.arange repetitions. And this is just a loop right now where the value I, ranges between now, because np.arange repetitions like defaults to 0, up to but not including this. Like I is going to go from 0 to 999, and we don't care at all about what I takes on. We just care that it's going 1,000 times. That's all we care about I for here. So some languages you just say, like when you're just using the loop to iterate a bunch of times and you don't care about using I ever. Some languages they say like for underscore, like just to imply like I don't care about this value. I'm just using it for looping purposes. That's kind of what we're using this loop for. Just like do the following 1,000 times, please. make a virtual pea plant garden. Give me how far away it was from our ideal 75-25 split. Let's see how much randomness can influence that split, even if it really was supposed to be from a 75-25 model. And then take that distance and append it to our distances array so we can keep track of it. Like that makes it a little bit bigger, but we also want to remember that for later. So distances equals that. If I do that, now I've got 1,000 virtual pea plant gardens, and I know how far away each of them was from the 75-25 split. In terms of absolute value, like how far off was it? And we want to know how often, right? How often was just randomness alone going to give us a garden that was this much off? Because that's what Mendel saw in real life. Does that make sense? Any questions about how we're doing this hypothesis test? We're just trying to see, like, all right, could it be due to chance only? Is this true? Yes.
Okay, so we're just making like 1,000 pea gardens in a way, just to see if it was good stuff.
We've made 1,000-ish pea gardens. Yeah, 1,000 exactly pea gardens. Excuse me, with 929 plants. Assuming what's that?
In each pea garden.
Yeah.
Okay.
929 plants in each of our 1,000 virtual gardens, and we've made that garden assuming this. Assuming the null hypothesis is true. That's exactly what we assumed, that Mendel's model is correct. So we made our virtual pea plant garden by randomly flipping a 4-sided die, and if it was 1 through 3, we said it was purple. If it was 4, we said it was white. So we exactly assumed it was really a 75-25 split. I made the garden in that exact way. And I've let randomness take over, because sometimes it won't exactly be always that. But randomness was the only factor involved here. And I've got those gardens, and I've got how far away they were from the exact 75-25 split distance. Does that make sense? That's what we've got. And so the question now is, all right, I've got all these distances. How often did I see something this far away? Because that's what Mendel saw in real life. If we're assuming his model was correct, even though we didn't see the perfect 75-25 split, this should still be capable of being generated by chance, if the null hypothesis is true. All right, so we want to see how many times, how often was it that far away, or more, right? And that leads into the idea of a p-value. So let's make a histogram first. Let's do an empty table with a column. And what do we want to call this? Like distance between our sample percentage and 75%. Those are our distances. And we can do a dot histogram on those distances. I don't know how many bins we want to use. 15 bins or so. How about that? We can do the default number of bins. It's probably fine, actually. So there they are. That looks cleaner anyway. And our goal is like, all right, these are our virtual pea plant gardens, and this is how often they were this far away from 75%. Or like 1% away, 2% away, 3% away, 4% away. What Mendel saw was about 1% away. Does that make sense? That's what he saw in real life. And this is gardens left to chance. Quite a bit of them had a split this far away, which is nice. This is implying that the null hypothesis can generate gardens that were that far off, as far off as he saw in real life, and still be a perfect 75-25 split genetically. Does that make sense? So we've kind of proved that. And not only that, like we've got this many over here, but we've also got things even farther away. And that is in the direction of the idea of our null hypothesis being incorrect. Even chance is generating sometimes pea plants that are like 71% purple, the rest white, 4% off, which is crazy, but that's good to know. All right, and so that leads into the idea of a p-value, because the p-value is you want to see how often, right? How often did chance generate something that the observed value or something even more extreme, right? Remember those words, that's important. So how often did randomness from the null hypothesis assumption generate the observed value, the observed distance, or something more extreme? Something even more extreme. And so that would be, all right, from about 1% onwards to a positive infinity distance. Like all these values, how often did random chance give us a value that Mendel saw, or even more extreme, even farther away from what we thought? And that's just chance doing that. And it looks like it's quite a lot, over half probably. Bless you. And so that's what we want. We want to say we've got observed distance here. How often did we see something in our distances that we generated? We can say distances. How often did we see something like equal to the observed distance, or even larger, even farther away, so greater than or equal to? How many of those did we see? And so that gives me a bunch of trues and falses. But what I want to do with those, right, is I want to say np.count non-zero. So give me all the trues. How many trues were there out of the repetitions? And that will give me the p-value. How many values in our randomly generated p-gardens? How many of our virtual p-gardens out of the 1,000? What percentage of them had a distance away from a 75-25 split as far away as Mendel saw, or even farther away? Because this is just due to chance. And over half of them did. And so that lets us conclude that, the null hypothesis is not so bad. I've generated things under the assumption that this is the driving factor. This is the one and only thing that's causing pea plants to grow purple or white. And just assuming only that, it accounts for what we saw in the real world so very often that there's a very good chance that it's a good model. Does that make sense? So we say we do not reject the null hypothesis. It's very likely for the null hypothesis to give us what we saw. Does that make sense? So that's our conclusion. We do not reject the null hypothesis. And that is our Mendel example. So we did a lot of things. We made some distances, picked a measure, right? That was the absolute value. How far away from 75% do we need? Because it didn't matter on either direction. It's like, all right, was it 76 or was it 74? I don't care. It was far away from 75. That's what we wanted. So absolute value was necessary there. And yeah, we got a p-value out of this deal. And I think that's what I wanted to say. Any questions about that? Do you see it? Is it coming back to us? Was it never gone anyway? So yeah, that was a hypothesis test. Are you ready for another? So we also need to do, that was sample proportion stuff. Let's also do one where we do a permutation test, and so where we flip around labels and stuff. So let's do my favorite cereal data set example. And so we saw that the cereals on shelf 2 in our cereal data set, they were pretty darn sugary, more so than the others. And so we want to test, maybe that was just random chance. People were randomly putting different cereal boxes on shelves, and it just so happened that the random cereal boxes that were placed on shelf 2 were extra sugary. And that could be a null hypothesis. Does that make sense? Because that's very easy to generate. Just take all the cereals, pick who gets to be on shelf 2 randomly. Does that make sense? Do that a bunch of times. See how often you found something as sugary as the real life version of shelf 2. Yeah? And that leads to the alternative hypothesis of the idea where, something is off. It's not just the null. Maybe the shelf 2 cereals were more sugary. All right? And so this gives us a different idea here. The alternative hypothesis for Mendel is it wasn't 75. It was something away from 75. But for this one, our alternative hypothesis was it wasn't just not the same amount of sugar as we saw in real life. It was, it wasn't how do I want to say this? It didn't matter. We didn't want to, it wasn't just the case that it could have been less sugary, like these random cereals on the shelf. How often were they the value that we saw or even more sugary? Does that make sense? We care about more, not less, because we think that they're too sugary. Does that kind of make sense? So a directionality here is important in this question, whereas it wasn't really important in the Mendel question. Do we kind of see that? Again, it's subtle. Does that make enough sense? We don't care about more or less sugar. We only care about more sugar. We think that there's something off and it's in the direction of more sugary cereals on shelf 2, not less sugary, more. And so absolute value is something we shouldn't be using here when we make a distance calculation. Like how far away was it in one direction? I want positive and I want negative as well now. Does that kind of make sense? And I'll show you that when we get to it. But that's something we did. And we can use a permutation test to make this happen, though, once we make this happen. And so, yeah, let's do... Let's do the average sugar content on shelf 2. That's kind of the value we care about here. So cereal, so let's read the data set. So here's all my fun cereals. We can, let's just deal with, we care about the cereals in terms of sugars and what shelf they're on. So let's select out just those 2 columns to make it easier for ourselves. Cereal.select. Give me the shelf in that order, then the sugars. So there's shelf 3, shelf 2. So those are all the cereals. And then we can do a group by, so group by shelf. And there's similar amounts except for shelf 3 for some reason. That's just by counting how many are on which one. But we want to aggregate the values on shelf 2 by not the count, not by the number of things in that sequence, because it's like bringing them all together as like an array or something. Like, give me the array of cereals on shelf 2, give me the array of cereals on shelf 1, give me the array of cereals on shelf 3, and then do by default the len calculation. Tell me how many there were. But we can say no. Do the average calculation, np.mean, np.average. So this will give me the average sugars for all the cereals on shelf 2 and all the others. And we see that there's a huge gap here. There's a huge issue with shelf 2. And I hope you see that. So our question is, our hypothesis test now is like, okay, maybe we'll give them the benefit of the doubt, right? Give the supermarket the benefit of the doubt. Maybe just randomly they were picking cereals and they just so happened to put a lot of sugary cereals on shelf 2 randomly. We can generate that. Does that make sense? We can generate that and see what happened. And we'll just keep track of when we generate, so that's what we're going to do. We're going to do a permutation test, and we're going to use the average amount of sugar in our virtual shelf 2. Does that make sense? Like, that's what we need here. There's no absolute value or subtraction. Let me just say this here. We'll use average sugar content on each shelf, and we want to know if it's like less or more. We want to know, not absolute value, which direction was it, because we think things are more sugary on the shelf rather than less. So, yeah, let's do that. The way that we do this test, one of the easiest way, is to do a permutation test. And what a permutation test is, right, is we've got a bunch of cereals here. We have sugars, we have what shelf they're really on. What we'd like to do is pick a random shelf 2. Does that kind of make sense? We want a random shelf 2 out of all these cereals, and one easy way to do that would be to like take the shelf column. It's got a bunch of 3s and 2s. It's got the amounts that were on the actual shelves. If I shuffle those and assign new, then I could use those shuffled labels of shelf to assign new shelves to those same cereals. Does that make sense? That's what a permutation test is all about. If I shuffle the labels, I can pick new shelves for all these cereals, and I can see I can make a new virtual shelf 2. And because it was shuffled randomly, it's me picking a shelf 2 completely randomly, like according to the null hypothesis. That's me generating that. All right. So that's how we can do it. It'd be like cereal dot, let's see here. If I do dot sample, right? If I do cereal dot sample, and I have to take the same shelves, right? I want the same amount, like the same, like 21 things on shelf 2, 20 things on shelf 1. So I say sample all the values, the same number of rows. By default, it's like that, but with replacement equals false. Right, so it's got to be with replacement equals false. That's going to shuffle all of the rows of the cereal table. All right. with replacement equals false is going to not duplicate 100% brand twice or anything. It's going to keep the same cereals, and they're just going to be in different orders now. So it's going to not replace anything. Keep all the same ones there, the same amounts and everything. And then I want the shelf column of all that. Because it was like a bunch of 3s and a 1, 2. If I do it like this, now these shelves are in different orders. See that? These can be my new shelf labels for my virtual supermarket. It's like that. That's kind of what I want to do here. I want to be like cereal, add a new column called like shuffled label. That's what we did before. Because now, like, all right, this old cereal was on shelf 3. It's going to still be on shelf 3. This old cereal was on shelf 3. Now it's going to be on shelf 2. See that? So sometimes they're going in different places. This old cereal was on shelf 2. Now it's in shelf 1. Like, here's a new shelf 2 cereal. It used to be on shelf 3. So like, this is a random assignment of shelves for each of these cereals. And this was just one random assignment. So I can get the average sugars now on this, right? I can get the average sugars for this new ordered by shuffled label. And that's like another random shelf too. And I can see how much sugar was on that random shelf. Does that make sense? So if it was due to randomness, I will see a value this large sometimes for random shelves, random shelf 2s. Does that make sense? That's what we're going to do. How many times can I play this game where I'm shuffling labels and picking new rows randomly, completely randomly, right? That's what the null hypothesis implies. Picking completely random shelves for these cereals. How often do I see a value this high or higher? Not lower or higher, right? The direction matters here. So we think it was this sugary on purpose, right? Not less sugary. So that's what we're going to do. So let's make a function that gives us back, all right, make me a random supermarket shelf 2. Give me the average sugars on that, average sugar content of the cereals on that random shelf. That's me pretending the world is just like the null hypothesis says, and give me back the sugars. Let's see how often we got a value as extreme or more extreme than we saw compared to the one we saw in real life. All right, so I'm gonna make a function called give me one sample, not distance, an average. Give me average sugar content on shelf 2. Cool. So I want to do this. I want to make this exact thing. I want to make a new shuffled table, just like this. And I can call this, I guess I can do it in one line. Why not? So I would like to, this is a new, let's go further here then, if we're going to do it this way. So here's like my simulated table. I can then do a dot where. I'm going to treat these cereals by their shuffle label. That's the shelf that they're on now randomly. Where the shuffle label values are 2. So that gives me all the new shelf 2 items, right? Where the shuffle label is 2. Some of these used to be on different labels. Like this one was on shelf 1, this was on shelf 3. This is its new shelf. These are all the new shelf 2 items, just randomly chosen from other potential shelves, just everywhere else in this store. And then I want the sugars column for those now. And like, give me the average. That is the sugar amount for a random shelf 2. Does that make sense? If I rerun this, it gives me a sugar amount for another random shelf 2. Does this code make enough sense to us? We're shuffling labels, getting the new shelf 2, the new random shelf 2. Give me how many sugars were on that. How much was the sugar content of that new random shelf? So we're simulating the world under the idea that the null hypothesis is the only thing driving the sugar content of cereals on shelf 2. Does that make sense? And that's a permutation test because we're permuting the labels. Permuting the labels, and so like this is all I need then. It's like return this. And I gotta make the indentation correct, of course. But there, just do exactly that. I got a bunch of averages that way. All right, and so I can play the same game of simulation. So like, do this whole thing we'll just type it out just for fun. So how many simulations do I want to do? I did repetitions last time. Let's do another 1,000. The more the better though. Like do 10,000 if you can. and then I'll make a bunch of sample averages. I'm going to simulate the world 1,000 times. I'm going to make 1,000 different shelf 2s randomly, according to our null hypothesis, because it's due to randomness was the sugar content, what we saw. I'll make a bunch of random shelf 2s and keep track of the average sugar content of each of those shelves. I'll keep track of a bunch of sample average values in a sample averages array. I'll say for I in np.a range, number of simulations I'm doing right now. I would like to say one sample average and add that to my list. Like keeping track, that's another simulated value. Plop it into sample averages, please. np.append sample averages, that value. Boop, just like that. And in the blink of an eye, or slightly longer because it's got to do some shuffling, I've got a bunch of sample average values. I've got for a bunch of random shelf 2s where I'm assuming that really the sugar content was due to randomness. Like there's nothing else. I was just randomly picking, just like blindfold taking cereals out of the loading cart and putting them on shelves arbitrarily. That's what we're assuming right now. So that's what we've got. Are there any questions about the array of values that we've generated so far and how that's going to match the idea of our null hypothesis being true? And so the value that we chose, the number that we're holding on to, is the average sugar content in this random shelf 2. We're not subtracting it, or we're not doing an absolute value comparison against the real life shelf 2 or anything like that, because that wouldn't tell us was there more or was there less. Absolute value gets rid of that idea. We really do want directionality here. We want to know like how often, right? For our p-value example for that. Like how often, we're going to make a histogram, how often did we see a value as sugary or sugarier than this, right? In the direction of more sugar. That's more extreme, not less. So absolute value would have ruined things for us. So yeah, let's make another table with a column, averages, and we're going to put our sample averages there. And then let's do a histogram over that. With, I don't know, by default, the histogram just makes a histogram of the only column. If there's only one column in the table, you just say .hist. But if you want to be very specific, like do a histogram on column 0, please. Like that's going to be the same thing. And of course, you can change the number of bins that it creates. Let's do 20 bins. I don't know, something like that. And so that's almost a normal distribution, isn't it? So let's see. What was the value we saw, right? We saw, in real life, it was 9.61905. That was the average sugar content on shelf 2. Do you see how in our 1,000 simulations of shelf 2, we kind of usually gravitated towards a sugar average of 7 grams, I guess, something like that per serving. 9 is way over here. Something even more extreme than 9 would be that way, right? In that direction. We kind of want to count now for our p-value purposes. We want to count how often do we see a value this extreme or more extreme in the direction of more sugar. It's like how often do we see something here or onwards? Does that make sense? Because that would be randomness generating something like that or worse. Yeah? It seems like it's not very often. So that's what we're going to check now. How often on our sample averages, how often were they equal to 9.61905 or bigger? That's in the direction of more extreme, causing us to believe our alternative hypothesis is true. Right? That's the direction that you calculate your p-value, and we cared about direction here. So that's why we didn't use absolute value, and we want to count how often was that true, np.count non-zero, and then we'll divide by the number of simulations. That was simulations, or just it's 1,000. How can we get that another way? Like sample averages had 1,000 things in it. Could have done over lens sample averages. That's another way to get 1,000. And it looks like we've got, it only happened about once. 1 out of 1,000 times ish. So that's kind of funny. And that shows us that it is, all right, if we were to assume that it was just a random shelf 2, the null hypothesis was true, we only 0.1% of the time would see a shelf that sugary. It's very, very unlikely, extremely, extremely unlikely that this was a random shelf because of that. Does that make sense? Yeah. So our conclusion then would be, we reject the null hypothesis. Usually the cutoff is about 5%. That's statistical significance. This is even worse than 5%. It's less than 1. Like, it is significantly, it's extra significant. So here we reject the null hypothesis. It's very unlikely for our null hypothesis model to predict what actually happened, and so we're going to assume that we were wrong, and that we should be we are going to agree more with the alternative hypothesis because of that. Okay, and so that would be our conclusion here, and I think that is what I wanted to say. Are there any questions about this example? This was a permutation test where we shuffled labels. We did not use an absolute value because we cared about a direction when we were coming up with, like, what was the value that we're going to generate here. So that was important. Another, what could we have done? Another number that we could have generated is we could have compared against this 9 value, 9 point whatever value. We could have taken this value and could have been like, return that, like, minus that or something. Does that kind of make sense? Like, that would have also worked, but we just can't use absolute value because now we want to look for values equal to 0, right? Because that means it would have been the same random amount, or even more sugary, so like 0 or more positive. Like the value that we get back has just been shifted around. Like, that's still fine. We couldn't have used absolute value because that would not have told us the direction anymore. Yeah, I think I've said that in as many different ways as I can think. Yeah, I think that was my serial example. Are there any questions about that? Because I think that was probably enough for today. We have 10 minutes left. I don't think I can finish the next example in 10 minutes. So let's stop there for the day. The next thing we'll get back to next time is we'll do the bootstrapping idea where we're taking samples out of thin air. We got one good sample. Let's pretend that we sampled the population some more. That's what the bootstrap gives us, right? And then we'll generate some confidence intervals from that using another friendly function that we know and love, the percentile function, right? We're going to need that to do confidence interval calculations after we make some simulations. So that is what you can look forward to. Honestly, I'm going to give you these slides, so try to do it yourself. That's the best way to study, I would say. But we will come back on Wednesday and start there and go over that. And we got regression, we got classification, we got chapter 18. That's Bayes' rule, where you're calculating percentages based on some new knowledge. So given something, how does that change the layout of everything? So yeah, those are all the chapters I care about. Then I have some more examples after that from the book. So that's where we're going to go. Are there any last questions that you would like on the recording before I let you study and or work? All right.